July 4th, 2012, CERN. Two experiments, ATLAS and CMS, both announce independently that they've found it, the Higgs boson. 50 years of theoretical prediction, decades of experimental searching, billions of dollars of machinery buried under the Swiss-French border, physicists crying in the auditorium, a genuine moment of triumph. And then, once the champagne was opened and the headlines settled, a quieter realization began to spread through the physics community. The mass they measured was 125.09 giga-electron volts, and that number, that specific, precise number, didn't close the story. It opened a problem so sharp, so precisely defined, that the standard model has no answer for it. Finding the Higgs was supposed to be the end. It turned out to be the most exact statement yet of what we still don't understand. Before I can tell you why the mass is strange, I need to tell you what the Higgs actually is, because the popular version is almost entirely wrong. The God particle. That phrase came from a book title, Leon Liederman's, whose publisher wouldn't allow the original name, which was considerably less flattering. It is not a physics term. It has never been a physics term. Forget it. Here's the real picture. The Higgs boson is not the primary thing. The Higgs field is the primary thing. The Higgs field is a quantum field, like the electromagnetic field, but with a crucial difference. In the vacuum, the electromagnetic field is zero. No charges, no currents, the field is quiet. The Higgs field in the vacuum is not zero. It has a constant, non-zero value everywhere in space, always. Even in the emptiest region of the universe, the Higgs field is switched on, and particles moving through that field interact with it. The strength of that interaction determines the particle's mass. A photon doesn't interact with the Higgs field at all. Zero coupling, zero mass. The top quark interacts very strongly. It's the heaviest known elementary particle. The W and Z bosons interact in a precise way that's connected to electroweak symmetry breaking, the process by which the electromagnetic and weak forces separated as the early universe cooled. The Higgs boson itself is what you see when you disturb the Higgs field violently enough. Like a wave on the ocean is the field, the wave is the boson. You need a lot of energy to excite the wave. That's why it took a 27-kilometer particle accelerator running at 13 trillion electron volts to produce it. One thing worth saying plainly, the Higgs field does not give everything its mass. It gives elementary particles, quarks, leptons, the W and Z, their mass. Protons and neutrons get about 99% of their mass from the binding energy of the strong force, from Q, C, D. The Higgs contributes only a small fraction of the mass of ordinary matter. Your mass is mostly strong force, not Higgs field. The Higgs is essential, but the story is more complicated than the popular version admits. Now, the mass. 125.09 giga-electron volts. On its face, this seems like a reasonable number. The proton has a mass of about 0.938 giga-electron volts, so the Higgs is about 133 protons worth of mass. Heavy, but not the heaviest particle we know. The top quark comes in around 173 giga-electron volts. The strangeness is not in the size, it's in the location. There are two important energy scales in physics. The electroweak scale, the scale at which the weak and electromagnetic forces become comparable, where the Higgs field does its work, sits around 100 to 1000 giga-electron volts. The Higgs mass, at 125 giga-electron volts, lives comfortably in this range. That's expected. That's where it belongs. The other scale is the Planck scale, around 10 to the power of 19 giga-electron volts. This is where gravity becomes as strong as the other forces, where quantum gravity must become relevant, and it is 17 orders of magnitude above the electroweak scale. In quantum field theory, particle masses receive quantum corrections. Virtual particles, loops in Feynman diagrams, contribute to the measured mass of the Higgs, and those contributions are sensitive to the highest energy scale in the theory. If the theory is valid all the way up to the Planck scale, and we have no confirmed reason to think it isn't, then those corrections are of order 10 to the power of 19 giga-electron volts. Enormous, much larger than the 125 giga-electron volts we observe. So the bare Higgs mass, the hypothetical Higgs mass before quantum corrections, and the quantum corrections themselves must cancel, not approximately, to 1 part in 10 to the 17th power, 17 decimal places of cancellation, spontaneous, unexplained, built into the standard model by hand, invisibly, with no mechanism to enforce it. This is the hierarchy problem. Let me make it concrete. Imagine two numbers, each of the order of 10 million trillion. You add them together. You get 125. That's the level of cancellation the standard model requires for the Higgs mass. Not because any symmetry enforces it, not because any principle demands it, just because. The numbers happen to cancel to 17 decimal places, and no one knows why. Physicists are not comfortable with unexplained cancellations of 17 decimal places. So they invented solutions. The most celebrated is supersymmetry. The idea: every particle has a superpartner, a particle with the same mass and charge but different spin. When you calculate quantum corrections to the Higgs mass, the contributions from particles and their superpartners cancel exactly. The fine-tuning disappears. The hierarchy becomes natural. Supersymmetry is mathematically elegant, appears naturally in string theory, and provides dark matter candidates as a bonus. Before the LHC turned on, a significant fraction of the theoretical physics community expected to find superpartners. They would need to exist at energies of roughly 1 to 10 TeV to solve the hierarchy problem naturally. The LHC has searched those energies comprehensively. No superpartners, none. Compositeness was another idea. Make the Higgs not an elementary particle, but a composite one, built from more fundamental constituents bound by a new force. Composite Higgs models naturally generate a light Higgs without fine-tuning. The LHC has found no evidence of Higgs compositeness. The Higgs behaves, in every measurement so far, like an elementary particle. Extra dimensions. If gravity leaks into additional spatial dimensions invisible to us, the true Planck scale might be much closer to the electroweak scale, eliminating the hierarchy entirely. The LHC has found no evidence of extra dimensions. Every solution, each one motivated, each one mathematically developed over years of work, has so far failed to appear in the data. The LHC has not been silent about the Higgs. It has told us a great deal about it. What it has been silent about is everything we expected to find alongside it, which leaves a possibility that before the LHC results, most physicists preferred not to dwell on. What if the cancellation is real? What if the Higgs mass is simply fine-tuned, a coincidence of extraordinary precision with no mechanism behind it. This path leads toward the anthropic argument. If the Higgs mass were much larger, say comparable to the Planck scale, then electroweak symmetry breaking would produce a completely different mass spectrum. Atoms as we know them might not form. Chemistry might not work. The universe might be a structurally impoverished place where no one asks questions. In a multiverse, a collection of universes with different values of physical parameters, we necessarily find ourselves in a universe where the Higgs mass permits our existence. No mechanism required, just selection. We observe the value we do because only universes with roughly this value produce observers. I want to be honest about this position. It is logically coherent. I find it deeply unsatisfying, and I think that dissatisfaction is scientifically legitimate, not merely aesthetic. Explaining why we observe a value by saying only this value permits observers is not the same as explaining why the value exists. Selection arguments tell you about the observation. They say nothing about the mechanism. And physics, at its best, is the search for mechanisms, for reasons, not just consistencies. The multiverse is currently untestable. It may remain untestable. A framework that cannot be tested is not wrong, but it is not, in the usual sense, physics either. This is where the field honestly sits, between a fine-tuning that demands explanation and a multiverse that cannot provide one in experimental terms. There is one more thing the Higgs mass controls that most people don't know about. When you take the measured value of the Higgs mass, 125.09 giga-electronvolts, and combine it with the measured mass of the top quark, about 173 giga-electronvolts, and run the calculation of how the Higgs field's potential energy behaves at very high energies, something uncomfortable emerges. The Higgs field has a potential, a shape in field space, and our universe sits at a minimum of that potential, the electroweak vacuum. But calculations suggest that at very high energies, the potential develops a second, deeper minimum. Our vacuum may not be the ground state. It may be a metastable state, stable for enormously long times, but not permanently stable. If this is correct, a quantum fluctuation could, somewhere in the universe, nucleate a bubble of true vacuum, a region where the Higgs field transitions to its lower energy state. That bubble would expand at the speed of light. The laws of physics inside it would be different from the laws outside. Everything the expanding bubble encountered would be converted. No warning, no signal preceding it. It travels at the speed of light, so nothing outruns it. The calculation places our universe in a region called metastable. Not certainly unstable, not certainly stable. The boundary between stability and metastability passes almost exactly through the measured values of the Higgs and top quark masses. We are balanced at an edge, possibly permanently, possibly not. And the Higgs mass, that specific number, 125.09 giga-electron-volts, is one of the two numbers that places us there. 125.09 giga-electron-volts. That is what the universe offered us after 50 years of searching, after the largest scientific instrument ever built was aimed at a single question. That number gives elementary particles their mass. It sets the scale at which electroweak symmetry broke in the early universe. It determines whether atoms form and chemistry works. It sits in a position of extraordinary fine-tuning that every proposed natural explanation has so far failed to account for, and it places the quantum vacuum of our universe, the foundation on which all physical law rests, at the edge of stability. We found the Higgs, we measured it with precision, we understood its role, and the more precisely we understood it, the more precisely we defined what we do not know. Why is it 125 gigaelectron volts and not 10 to the power of 19 gigaelectron volts? Why does the cancellation occur? Is the vacuum stable? Is there physics beyond the standard model, waiting at some higher energy, something the LHC hasn't reached? Or are we alone at this scale, with only fine-tuning beneath us? The Higgs boson was supposed to complete the standard model, complete the picture, close the ledger. Instead, it handed us a number. And then, with the quiet precision only nature can manage, it asked us whether we understood why. We don't, not yet. And that gap between knowing the number and understanding the number is where physics lives right now.